Good plan, right? All right, so master plan for the day today is we're going to be discussing stoichiometry. Now, before we talk about stoichiometry, I want to give you an analogy that describes the process that we are going to go through. And in order to discuss that, I want to talk about making smoothies. You guys have all made smoothies at some point or other before, right? The perfect recipe for making smoothies, as I have discovered through many, many years of painstaking research, is you combine 2 bananas with 1 strawberry and 3 milks. Not sure what the units on that are, but just 3 milks. Okay. In order to make 1 smoothie. Sound reasonable? Okay. Now, looking at the smoothie making from this perspective, this recipe that I've written here looks more or less like a chemical equation, right? And the idea behind the calculations we're going to be making today is that we are going to be combining together 2 things you already know how to do. We're going to be combining together the ability to set up a monorail to make a calculation with the idea of a balanced chemical equation describing the relative ratios the reactants combine together in to make a product. And in combining together those 2 ideas of monorails and balanced chemical equations, we can use these tools to make predictions and calculations of the amounts, the relative amounts of reactants and products that we're going to need to make a chemical reaction work. So let me give you an example here. Let's say here, folks, that I was going to go to the store and I pick up 36 bananas. The question I have for you is, if I buy 36 bananas, how many milks am I going to need to buy in order to use up all 36 of those bananas in making my smoothies? Okay. So the idea is as follows. Recognizing that from my balanced chemical equation, I know that there is a ratio of 2 bananas consumed to every 3 milks consumed. If I start with 36 bananas and set up a monorail, I feel like we need that for the whole class. This is for posterity here, folks. 1, 2, 3, monorail. There you go, much better, thank you. I'm sure that Miss Martin's blocks will appreciate that. Okay. All right, so if we have 36 bananas, and I know that for every 2 bananas consumed, we consume 3 milks, that would tell me that, canceling out my units here, 36 times 3 divided by 2, I would need to purchase a total of 48 milks to completely consume all of those 36 bananas. So far, so good. Now, by that same logic, I could set up another monorail that would say, if I, again, had 36 bananas, how many smoothies would I need to, could I make given those 36 bananas? And again, setting up a monorail. Monorail. I said 54. Thank you very much. First error in our recording for posterity here. All right, so if we have 36 bananas and we wanted to know how many smoothies we can make, at this point, my ratio of bananas to smoothies would be a ratio of 2 bananas consumed for every 1 smoothie produced, right? So setting up my monorail then, 2 bananas consumed produce 1 smoothie, and therefore 36 times 1 divided by 2 gets me a total of 18 smoothies could be produced from a total of 36 bananas. All of this tolerable? All right, so the idea here is this. Given a balanced chemical equation, we can use that balanced equation's coefficients to describe the relative ratios of the numbers of reactants and products that are consumed and produced in the course of a chemical reaction. And as those ratios hold true no matter how much of the substances you're reacting, we can use those ratios as essentially what we call a mole ratio or a stoichiometric ratio in order to make calculations involving the relative amounts of reactants and products that we would use in a chemical equation. Okay. Now, the important thing to note here, and please be very, very careful, these ratios described within this recipe right here are ratios of numbers of items, right? It is the number of bananas compared to the number of strawberries compared to the number of milks we would need. They are not ratios of the masses. So just because I happen to need 2 bananas to 1 strawberry, that doesn't mean I need twice as much mass of banana in comparison to 1 mass of strawberry, right? And as such, if I give you units of mass, in order to use this tool, setting up these monorails to make these calculations, you cannot set these ratios up as mass ratios. They must be set up as ratios of numbers of particles. And you already know where this is going at that point then. If you get a mass, you need to convert it into a number of moles such that you can use those ratios from the balanced chemical equation. Now, this idea that we've just talked about right here is what we refer to as stoichiometry. Stoichiometry is the use of a balanced chemical equation to make quantitative predictions about the relative amounts of reactants and products that are consumed in the course of a reaction. And the process of stoichiometry is dominated by our ability to recognize a mole ratio or a molar ratio. That is the relative numbers of particles that are consumed or produced as described by the coefficients within a balanced chemical equation. And that right there tells us pretty much the most important thing we're looking at here is that in order to use stoichiometric calculations, your equation absolutely must be balanced. If it's not balanced, none of this works and everything falls apart. Okay. So, with that being said, we're going to go ahead and start off here with some really, really friendly problems, and then we'll move on to a couple of less friendly ones as we go. First examples here, I just want you to get used to looking at this chemical equation as a representation of the mole ratio of the reactants in the products. So let's take for an example here, if we have the equation written on the board in which we have 8 hydrogen molecules combining together with an S8 molecule to form 8 molecules of hydrogen sulfide gas, H2S. This first set of questions I'm going to ask you are very straightforward. They're simply about the mole ratios described within this equation. What's the mole ratio of hydrogen to hydrogen sulfide described by this balanced equation? For every 8 moles of hydrogen that are consumed, we produce 8 moles of hydrogen sulfide gas. Now, mathematically speaking, that 8-to-8 ratio is exactly the same thing as a 1-to-1 ratio. So it doesn't matter in your balanced equation if you have an 8-to-8 or a 1-to-1 there. The math of the stoichiometry will work out the same since those two are mathematically equivalent to each other. All right, second question here, what's our ratio of hydrogen to sulfur described by this balanced equation? For every 8 moles of hydrogen that are consumed, we consume 1 mole of sulfur, right? We have an 8-to-1 mole ratio of hydrogen to sulfur. And likewise now here, our mole ratio of hydrogen sulfide, the product, to sulfur, for every 8 moles of H2S that are produced, we consume 1 mole of S8. Okay. So again, those mole ratios are essentially the ratios of the coefficients from the balanced chemical equation. All right, now with that being said here, let's go ahead and take a look at a very straightforward, easy example problem, and then we'll do a couple of hard ones, and then we'll give you time to work. So, the equation we're going to deal with now here is the reaction written up at the top there, in which we're taking 2 molecules of hydrogen, combining together with 1 molecule of oxygen, to produce 2 molecules of water. What type of reaction is this here? Synthesis, absolutely. This is a synthesis of water. We could also make a case for a combustion reaction as well, since we're essentially burning hydrogen fuel here in the presence of oxygen. All right, now the first question I have here for you is a mole ratio question. What is the mole ratio of hydrogen to water described by this balanced chemical equation? 2 to 2, right? So for every 2 moles of H2 that are consumed, we would produce 2 moles of H2O. Now, with that ratio being said here, in part B, suppose I gave you 20 moles of hydrogen gas, and you had plenty of excess oxygen to react as much as you needed. How many moles of water could you make? It's exactly as straightforward as it looks, right? Given that for every 2 moles of hydrogen that are consumed, we produce 2 moles of water, if you had 20 moles of hydrogen, you could logically produce 20 moles of water. Now let's take a look at what this is going to look like in terms of our mathematical setup from a monorail. Here we go, 1, 2, 3. Monorail, very good. On the upper left-hand corner, we are starting with 20 moles of hydrogen gas. Now, within that monorail here, remember our mole ratio is nothing more really than a conversion factor at this point. It tells me how many moles of hydrogen there are in comparison to how many moles of water we can produce. So I can use that conversion factor as a step along the monorail. On the bottom here, I know that 2 moles of hydrogen gas consumed produce 2 moles of water, H2O, as a product. And canceling out our units here, very straightforward. Moles of hydrogen cancel with moles of hydrogen. I'm left with moles of water. That tells me exactly what I predicted. We can produce 20 moles of water given that amount of our reactants. So far, so good. Easy peasy. All right, so slightly more complicated, still pretty friendly though. What's our oxygen to water molar ratio? For every 1 mole of O2 consumed, we produce 2 moles of H2O, right? We've got a 1 to 2 molar ratio. Now, given this ratio, I'm going to ask you the exact same question we just went through there. Now, if you have 20 moles of oxygen and plenty of excess hydrogen, how many moles of water can you make? So again, setting up a monorail. Very good. This time we're starting with 20 moles of O2. And before we even set up the monorail here, folks, tell me, what should the answer be? Okay, now, the answer should be 40 given our logic, right? Because if we have 20 moles of oxygen, and we know that for every 1 mole of oxygen we produce 2 moles of water, we should be able to produce double the amount of water in comparison to how much oxygen we actually had, right? But do take the time to set up these monorails in this, because a lot of times people get tripped up in terms of when they multiply and when they divide. The entire purpose of that monorail is to remove that question from your brain about whether I should be multiplying or dividing here by canceling out the units properly. Okay. So if we know my molar ratio told me for every 1 mole of O2 that are consumed, we produce 2 moles of H2O. Moles of oxygen cancel with moles of oxygen, and we get 20 times 2, which tells us our logical answer here was 40 moles of H2O can be produced. And so far, so good? Smiling faces? Awesome. All right, now here's the problem. For these problems here, I gave you initial amounts of moles of each of these species, right? But nowhere in our laboratory do we have a device which measures moles. There's no such thing as a molometer, right? So given that I cannot directly measure moles in the laboratory, I can measure a bunch of different quantities like, say, masses or volumes or numbers of particles. So given that I can measure things within the lab, but I cannot directly measure moles, in order to use these ratios, we're going to start by needing to make a conversion from whatever given measurement we made in the lab into units of moles before we can use a molar ratio. Which essentially means these stoichiometry problems are going to end up looking more or less like a combination of what we've just done right here, combined together with a mole map problem. So let's go ahead and take a look at a couple examples that are slightly more complicated than the ones that we have done so far. I'm going to skip that first set of notes here for a moment here. We'll do a problem first, then we'll kind of go back and generalize after having this example. So, given our reaction here, this is a mess of nomenclature for you here. Given the reaction, let's see, we've got 4 iron 2 dichromates combining together with 8 potassium carbonates and 1 oxygen molecule to form 2 ferric oxide molecules, 8 molecules of potassium chromate, and 8 molecules of carbon dioxide. How many grams of ferrous dichromate are required to produce 44 grams of carbon dioxide? Okay. Now this is getting rapidly more complicated, and the best suggestion I can make to you as you're solving these problems, and this is something I'd like you to get in the habit of doing now so that as things get more and more complicated over the course of the year, you're in this habit. Whenever you set up one of these monorails, the absolute most essential thing you can do is to write down in every single step along the monorail both the unit and the species of every single thing that goes into your monorail. because if you do the math on the units and species, if it comes out canceling out properly, it's going to tell you you did the problem right. So let's set up our monorail. It's going to be a big one here. 1, 2, 3. Monorail! Very good. And let's come up with a plan of action here. We've been given grams of carbon dioxide. Given that we have grams of carbon dioxide, the ratios described within this equation are not mass ratios, they are molar ratios, which means the very first step we always need to do is convert into moles. So we're going to convert from grams of CO2 into moles of CO2 using a conversion of the number of grams per mole, right? Otherwise known as the molar mass. So we use the mole map here to make a grams to moles conversion into moles of CO2. And once we're into units of moles of CO2, we know that for every 8 moles of CO2 that are produced, we consume 4 moles of the ferrous dichromate, which means we're going to use that molar ratio in order to make a conversion from moles of CO2 to moles of ferrous dichromate. Once we then have moles of ferrous dichromate, we're going to convert from moles into grams of ferrous dichromate using, again, a mole map conversion, the number of grams per mole of ferrous dichromate. Okay, so that's kind of our plan of action. Grams to moles, moles to moles, moles to grams. So, with that being said, let's just set up the monorail. We've got 44.0 grams of carbon dioxide. And the first conversion we need to make here is a grams to moles conversion, which means we need to calculate real quick here the molar mass of CO2. So let's make that calculation here. In 1 mole of carbon dioxide gas, we've got 1 mole of carbon and 2 moles of oxygen. Carbon's mass per mole is 12.0107 grams per mole. Oxygen's mass per mole is 15.9994 grams per mole. And you add these two values up together, and I believe you are going to get 44.0098 grams of CO2 per 1 mole. So far, so good. So the unit that needs to go on the bottom of a monorail to make things cancel properly here is 44.0098 grams of CO2 is equivalent to 1 mole of CO2. So far, so good. We've gone grams to moles. Next step on our plan was to go from moles of CO2 to moles of FeCr2O7. And that is our molar ratio from the balanced equation. For every 8 moles of CO2 that are produced, we consume 4 moles of FeCr2O7. So our 8 to 4 molar ratio. And then last but not least, to go from moles to grams, we need another molar mass, right? Now of the ferrous dichromate. This one I'm going to need your calculation help here, guys. I don't know this one off the top of my head. Let's see, we've got iron, chromium, and oxygen. There's 1 iron. Iron is 55.845 grams per mole. Chromium, there are 2 chromiums times, 51.996, I believe, grams per mole. And then oxygen, we've got 7 times 15.9994 grams per mole. $271.833. Perfect, thank you. Grams per mole of FeCr2O7. All right, so final step along the monorail here. We know that 1 mole of FeCr2O7 has a mass of 271.833 grams of FeCr2O7. And again, as you're making your calculations here, double check your work with those units to make sure things canceled out properly, because that tells you whether or not we did things right. So grams of CO2 cancel with grams of CO2. Moles of CO2 cancel with moles of CO2. Moles of FeCr2O7 cancel with moles of FeCr2O7. leaving us with units of grams of FeCr2O7. You guys can multiply out here, and it's essentially going to be like, what, 136-ish? Yeah, 135.8, yep. Okay, so and then 3 sig figs here, 136 grams of FeCr2O7. Real quick sig figs question. Does the molar ratio count towards significant figures? Why not? Are there kind of 8 moles of CO2 per 4 moles of FeCr2O7, or they're exactly 8 moles of CO2 to 4 moles? It's an exact ratio, right? And because significant figures are a reflection of the accuracy of measurements, if you have an exact calculation that's involved there, that does not contribute towards any inaccuracy and therefore doesn't count towards your significant figures measurements. Okay, so only measured values that introduce some amount of error contribute to the accuracy of your measurement. Okay. So far, so good? All right, so let's take that problem we just did now and generalize the procedural steps that we did there. We started off with an amount of the first substance, which in this case was carbon dioxide gas, right? So you're going to be given an amount of the first species. We'll call it species A. That amount could be in grams, it could be in liters, it could be in a number of molecules, whatever amount you happen to be given. The very first step was we converted from the amount into moles. And essentially, we're using a mole map calculation to make that conversion. Now, we need to make the conversion into moles because the stoichiometric ratios described from the balanced chemical equation are not mass ratios, they're not volume ratios, they are molar ratios, the number of particles present there. So amount into moles using the mole map. Then from moles of the first species, we go to the moles of the second species using the mole ratio from the balanced chemical equation. And please, please, please again, make sure that that equation is balanced. If the equation is not balanced, this all falls apart. Once we then have moles of the second species, we convert it back into the amount of the second species, whether it be grams, liters, or number of particles, again using our mole map. So essentially, mole map to get into moles, molar ratio to get from moles of the first species to moles of the second, and then the mole map again to get back into a unit that you can actually measure in the lab. And that's pretty much the path you're going to take every single time. All right, let's do one more example here, and I'm going to set you free to work some of these on your own. Let's see here. Part B here is going to set up a monorail to ask you how many liters of oxygen gas are required to produce 100 grams of ferric oxide. And let's make the assumption here that this is occurring under standard temperature and pressure conditions. Okay. Now this is again using our exact same reaction we used before. And let's think about our plan of action for this pathway before we start setting up the monorail here. We've been given, this time, grams of ferric oxide, right? So given grams, we need to start by going grams to moles, again using a grams per mole, a molar mass conversion, right? So we're going to go grams to moles, but this time it's grams to moles of ferric oxide. Once we have the grams to moles of ferric oxide, we can go from moles of ferric oxide to moles of oxygen gas using our mole ratio. And then from moles of oxygen gas, we can go into liters of oxygen gas using our mole map conversions from moles to liters that we talked about last week. Okay. All right, so let's set it up again here. We've got 100.0 grams of Fe2O3. Monorail! Let's do grams to moles first. So molar mass conversion. We've got iron and we have oxygen. Let's go ahead and add up for me here. We've got 2 irons per mole of ferric oxide and 3 oxygens. 2 times iron's 55.845 grams per mole, and 3 times oxygen's 15.9994 grams per mole. Add up those values and solve for me, please. 59.688 sounds perfectly reasonable to me. Grams per mole of Fe2O3. All right, so on the bottom, to cancel out units properly, there are 159.688 grams of Fe2O3 per 1 mole of Fe2O3. Now that we've got from grams to moles, next step on our plan was to go from moles of Fe2O3 to moles of O2, and that's our balanced chemical equations mole ratio. For every 2 moles of Fe2O3 that are produced, we consume 1 mole of O2 gas. And then last but not least, to go from moles into liters of O2, we need to know how many liters per mole there are of a gas under standard temperature and pressure conditions, right? And this sounds very much like a mole map problem you were doing last time. And if you remember that number off the top of your head, the molar volume of a gas at STP conditions is, there you go, there are 22.4 liters of O2 per 1 mole of O2 at STP conditions. And again, that was the conversion we gave you from your mole map last week. Again, canceling out units here, grams of Fe2O3 cancel out, moles of Fe2O3 cancel out, moles of O2 cancel out, leaves us with liters of oxygen. Make your multiplication across the top, divide by the bottom there. This is going to be what, like 6 or 7-ish? .013. And sig figs here. It's a tricky question. So 100.0 has 4 sig figs. This molar mass has lots of sig figs, right? Mole ratio doesn't count towards significant figures because this is an exact conversion factor. Does 22.4 liters per mole count towards sig figs? Are there exactly 22.4 liters per mole, or are there kind of 22.4-ish liters per mole? This is a measured value from the laboratory, right? If you take a mole of gas, it doesn't know it's supposed to occupy exactly 22.4 liters, right? So this is a measured value, which implies this does involve accuracy of measurement, which means we're limited to 3 sig figs here. So answer here should be therefore 7.01 liters of O2. Success. All right, now, big hint for you here, folks, in terms of how to be successful at these, especially on the test. I've been very, very careful along the way, labeling both the unit of measurement, like grams or liters or whatever, and the species for every single species that is involved here. Please make sure you get in the habit of doing that now, because later in the semester here, we're going to have these monorail conversions, which are going to be like 7 or 8 or 9 different stops along the monorail long. And if you don't keep things organized in that way, things turn to mush rapidly, okay? I will tell you that looking on people's tests, I see all the time monorail set up like this. It'll say like 2.3 grams, and then like 1 to 2, and then 158 to 3, and then like there's these numbers on here, and then I go back and look at their work, and their answer is wrong, and I have absolutely no idea why. And they don't either, because this tells you nothing, right? These ratios need to be described accurately so you can go back and check your work. And it'll help keep you organized, and staying organized in these problems is the #1 way to make sure you get them right. Okay? All right, folks, so that is the master plan here for how to do these problems. We have 12 minutes remaining in class. With those 12 minutes, I'd like you to get a head start on your homework assignment, because these do tend to cause people some amount of difficulty. You picked up on your way into the room here problem set 6.04. I would like you to get together with a partner. Your homework assignment is going to be problems number 2, 4, 6, and 8 out of 6.04. If you can try within the next 12 minutes to get through to at least A, B, and C, if you can get through all of 2, that would be good in the next 12 minutes here. That would be a good place to start. I will be able to answer questions as you have them. And otherwise, folks, please use this time wisely. Go to it. Time is yours.